Ladies and gentlemen, good morning, good afternoon. Welcome to today's sessions. Kicking off today, we have a fantastic keynote for you. Dr. Rupak Biswas, Director, Exploration Technology Director at NASA Ames Research Center. Dr. Biswas, the floor is yours.
Thank you, Lawrence. Thank you, Amit, for inviting me to give this keynote presentation. It is indeed an honor and a pleasure being here, albeit virtually. I was eagerly looking forward to the event last year, but I'm impressed how the organizers put together a comprehensive virtual event while being in an unprecedented pandemic. I do look forward, though, to an in-person event in the not too distant future. Again, like Lawrence said, I'm the director of the Exploration Technology Directorate here at Ames Research Center. So what I thought I'd do today is give you an overview of what we're doing in terms of research and development in quantum information science at NASA, and how this really emerging field is or promises to help NASA in the various missions that we do. So let me begin by highlighting what is occurring at the national level within the United States in quantum information sciences. In September of 2018, the Subcommittee on Quantum Information Science under the auspices of the National Science and Technology Council put together a national strategic overview document for QIS. I was one of the 2 NASA representatives on this committee. And the report declared that QIS is the next technological revolution. And here are some key quotes. And if you look at some of the highlighted quotes in there, it says that QIS arises from a synthesis of quantum mechanics and information theory, but that protocols and approaches are not yet invented, and that the federal government needs to encourage the development of QIS by cultivating potential end-user applications. And based partially on this report, the National Quantum Initiative Act was signed into law in the United States in December of 2018. So that kind of sets the stage and the impetus for doing quantum information sciences in the US. Here's a simple one-slide explanation of what is QIS, and I'm going to use an example to highlight its power and promise. So what we did at NASA was do a hardware benchmarking computation where we ran this benchmark on Google's 72-qubit bristlecone chip. And we also ran it on NASA's Electra supercomputer. This is the primary supercomputer for NASA. And for this benchmark, the bristlecone chip took less than 2 seconds, while it took 59 hours on the Electra system, which translates to almost 5 orders of magnitude less time and less energy used. So what this shows is that QIS has the ability to compute what could not be computed even if every atom in the universe were a classical processor. And we are talking about 10 to the 78 atoms in the universe. And if each of those atoms were a classical processor and they ran for the entire age of the universe, which is 13, 14 billion years, there are certain applications that we would still not be able to solve. For example, factoring is an example, certain material science applications. And QIS promises significant advantages for optimization and machine learning by harnessing some uniquely quantum effects such as superposition, tunneling. And then, you could also use QIS for some low energy consumption. So even if you might not be able to solve something faster, there are certain calculations you could do which would be considered green computations. So why does NASA care about quantum information sciences? So here are some few examples. And I'll talk about some of these later in my presentation, but we could use quantum enhanced machine learning for earth science data analysis, trying to understand some of the data that is gathered by NASA from observational observational satellites. We could do quantum simulations for materials that could help with aerospace applications such as aircraft or spacecraft. Mission planning and coordination, as well as allocation and scheduling, these are NP-hard problems. So you could use quantum methods to do optimization of such things. Quantum information sciences could play a huge role in NASA's Artemis program to go back to the moon or for Mars exploration. You could also use quantum technologies for secure airspace communication. I'll talk about that briefly as well. And air traffic management is, again, a huge optimization problem that is impossible to solve on classical systems. And could quantum information sciences play a role there? So here's a brief history of quantum information sciences at NASA Ames. And this is a busy slide, and I'm not going to go over it event by event. My primary purpose of showing this slide is that our QuaIL group at NASA Ames has been involved with and leading quantum information sciences for over 20 years. Some of the highlights that I'd like to point out is that we hosted the first Quantum Future Technologies Conference back in 2012. We formed this really innovative agreement with Google for doing quantum annealing. We hosted the D-Wave systems over several years, some of the largest quantum annealing systems in the world. We formed collaborations with other federal agencies like AFRL, IARPA, DARPA on advancing the state of the art in quantum information sciences. We worked very closely with Google and Rigetti, and we recently partnered with DOE on 2 of their quantum information science centers at Fermilab and Brookhaven National Lab. So again, this is just to highlight the history of work that we've been doing in QIS at Ames by this QuaIL group. So what is the R&D work that we do in the QuaIL group? So I thought I'd illustrate that as a stack of activities. So starting from the bottom, one of the primary things that we do is provide fundamental physics insights by our expertise in quantum mechanics. And that could help to co-design quantum hardware. Co-design is a concept that is very common in supercomputing, but we can do the same kind of partnership and collaboration with hardware vendors to advance quantum hardware. Above that, we have solvers and simulators. It could be physics-inspired classical solvers. It could also be high-performance computing quantum circuit simulators. A layer above, which is probably one of the most important layers, is all the software tools and algorithms that will be required. New quantum algorithms have to be designed that we are working on, but it's also the mapping of these algorithms onto the hardware, parameter settings, tuning, error mitigation, maybe look at hybrid quantum classical approaches, and then compiling these quantum algorithms onto the native hardware. From a NASA perspective, our interest is in the applications. At the end of the day, what we want to find out is what can quantum do for NASA that I cannot otherwise do using classical systems. So we have a major focus on various applications. It could be planning and scheduling applications, it's material science applications, fault diagnosis, machine learning, data fusion, all of that. And then finally, beyond just the quantum computing aspect, there is the communications and network piece of quantum. So it could be quantum networking. It could also be distributed quantum computing. So what I'll try to do today is kind of touch on all of these things that we are doing within the QuaIL group at Ames. So first off, as we all know, there is a wide diversity of quantum computing hardware with a variety of physical implementations. And this list that I'm showing here is by no means comprehensive or exhaustive, and I'm sure many more architectures will come out in the next few years. But as you can see, there's also already a variety of quantum computing hardware. There's superconducting chips like those from D-Wave, Google, IBM, and Rigetti. There's ion trap from Honeywell, photonic from PsiQuantum. We have QuAIL atoms that was popularized by Cole Quanta, and they actually have an experiment running on the International Space Station. And of course, there's doped silicons and others. And so as you can see, there are general purpose systems like universal quantum processors, as well as these special purpose systems. But our main role within the QuaIL group at Ames is not developing quantum hardware, but rather be engaged with a variety of key players by providing important insights and thereby leverage the hardware advances that occur to explore applications of interest to NASA. So I must talk about the quantum annealing work that we did, not only because we hosted one of the largest quantum annealers in the world for several years, but also how our research provided insights into more general purpose quantum algorithms for gate model architectures. So here's a picture of the D-Wave 2000Q system at Ames. Over the span of 7+ years, the system was periodically upgraded from about 256 qubits to over 4,000 qubits. And significant research was also conducted by our group, as well as by Google and our partners at other federal agencies. But fundamentally, what we feel proud of is our research deepened the quantum community's theoretical understanding of quantum annealing. For example, we demonstrated orders of magnitude performance improvements when D-Wave implemented some of the advanced annealing schedules that we had come up with. And I'll talk a little bit about that as well later. I must also mention the quantum supremacy work that we did with Google and Oak Ridge National Lab in 2019 that created quite a buzz in the quantum community. So we achieved quantum supremacy because we performed computations that were not possible on even the largest supercomputers. And this was a major collaboration with Google and with Oak Ridge. And we appeared on the cover of the Nature magazine in the October 2019 issue. And as part of this work, we developed a simulator called QFlex that has been open sourced. And we are about to release a more general purpose simulator as an open source, and that's called Hybrid Q. But even after all the work that we did with quantum supremacy, I'd be the first to acknowledge that it was only for a toy problem. Quantum hardware at this time is still too small for solving practical problems that are intractable on classical supercomputers. Because see, at the end of the day, some of the largest supercomputers in the world are very, very powerful, and they can solve a lot of problems by sheer brute force that a small quantum system cannot solve. So eventually, these quantum devices need to scale up and become more reliable for them to really beat the supercomputers on a realistic problem. So what do we do in the interim, though? I believe that there is an unprecedented opportunity to invent, explore, and evaluate quantum algorithms empirically. Even though we may not be able to implement them on quantum hardware, we can do a lot of work but empirically. And so at NASA specifically, what we are focused on is develop quantum and hybrid quantum classical applications for computational challenges in aerospace and earth sciences, and also algorithms and applications to enable safer, more ambitious, and greater time and energy efficient space exploration missions. So let me give some more examples of what we're doing. And let me start with the bottom of that stack that we talked about, the co-design with vendors. So as I mentioned earlier, the NASA QuaIL team works closely with groups building hardware. We believe that this can lead to rich areas of co-design where our understanding of quantum theory and the application focus of our investigations can suggest hardware features that could improve performance. Sometimes the hardware folks tell us that what we think is simple to implement is actually very difficult. But in other cases, the discussions lead to substantial performance improvements. In this case, for example, performance of the D-Wave quantum annealer improved by orders of magnitude once they were able to implement a feature that allowed more control over the annealing schedule, specifically allowing the user to pause the anneal. When paused in the appropriate region, the system is able to thermalize, thereby improving overall performance. We first confirmed this performance improvement on toy problems that matched the D-Wave hardware graph, matched the D-Wave hardware graph, but have since confirmed improvements on application-related benchmark problems in network optimization, scheduling, and information sharing. As another example of co-design, we developed a quantum approach to optimization that uses more general mixing operators, achieving orders of magnitude better performance than with simple mixing operators. Usually, these advanced mixing operators must be compiled down to a sequence of native gates. That is, the operators are directly implemented on a processor and carefully calibrated. Hardware designers make choices as to which native gates to implement and calibrate, as calibration itself is an involved process. Because each native operation takes time and these early quantum processors can keep their quantumness for only a short duration before decohering, it is advantageous to minimize computation time by being able to use native gates rather than having to compile to a sequence of gates. For instance, here, Rigetti has implemented natively and calibrated the mixing operators for certain special cases of the quantum alternating operator ansatz, and we have been able to confirm that this native implementation does indeed outperform compiled versions on simple scheduling problems. Rigetti engineers are currently working on implementing more complicated mixing operators suitable for other cases of QA/OA, particularly those required for the algorithm to address more difficult scheduling problems. So that's at the hardware level. Let's now talk about tools. So error mitigation enables the computation to keep its quantumness longer, as we all know, counteracting interactions with the environment, such as impurities in the chip, stray electrons, crosstalk between operations on nearby qubits, or interference from control lines that cause decoherence. Generally, error mitigation requires more qubits and longer computation times, resources that we want to minimize. So our work has enabled less resource-intensive error mitigation. As we all know, in order to run quantum algorithms, they must be compiled to the gate set and coupling connectivity of the hardware. The resulting compiled algorithm can be viewed as a schedule for the operations that need to be implemented on the chip. We were able to make use of state-of-the-art temporal planning approaches and software that NASA develops and uses for other purposes to compile quantum algorithms by phrasing both the hardware and the algorithm as temporal planning domain and instance, and then interpreting the output as a set of instructions. We have also developed very advanced simulators of quantum circuits that enable us to benchmark quantum hardware by comparing its output against what ideal hardware would produce, test models for the errors on the processors, and determine the limits of classical computations. These simulators were key to the quantum supremacy demonstration that I talked about earlier that we did with Google by not only confirming performance up to the limit of the supercomputer, but also what it would take for a quantum processor in terms of size, the number of gate operations, and fidelity of those operations to go beyond what even the largest supercomputers could do in a reasonable amount of time. I would also like to emphasize that quantum processors must be modeled as open quantum systems in which the qubits interact with the environment, and having a more accurate model of open quantum systems is important because those things differ from the idealized quantum systems that we read about in textbooks. Let me now move on to how QIS could benefit various NASA application areas. So of course, let me start off by highlighting what QIS promises for aeronautics. As you know, aeronautics is the first A in NASA. And here we did a lot of experiments where we used quantum annealing approaches to deconflict optimal trajectories for air traffic management. As we all know, air traffic management is a hard problem. And if you throw in the fact that there will be many more, such entities in the air as we go into more increased air traffic in terms of more transportation and cargo, but also UAVs and drones. and then you throw in the uncertainty from weather related, we are talking about a very hard problem. We have also looked at how QIS and how it might be feasible for it to address some of the cybersecurity of communication availability for air traffic of the future. How can I use quantum technologies to do assured communication when I have many more entities in the air? Like I said, in terms of drones and UAVs. So our current efforts are focused beyond this, where we are looking at quantum algorithms for material simulation with applications for batteries and energy storage, and also strategies to optimize information sharing when we have bandwidth limited autonomous settings, such as UAS. Let me now briefly talk about where we think QIS could support Earth science. NASA collects vast amounts of observational data about the Earth. Significant processing must be done to extract information out of this raw data, with machine learning approaches being applied to enable search, pattern recognition, segmentation, image reconstruction, and generation of super resolution images. Time series data are particularly challenging. Furthermore, sampling is often a bottleneck in machine learning approaches. So we have developed a hybrid quantum classical machine learning approach that is a quantum-assisted variational autoencoder for simulating search on NASA's MODIS Landsat images over time series data. So we have developed other quantum-assisted machine learning algorithms, and have also looked at using machine learning to optimize the parameter setting in quantum algorithms. And finally, for space exploration, we have been able to use quantum optimization approaches to solve small instances of hard operational planning problems, and also explored hybrid quantum classical optimization approaches that we tested on small problems that captured certain aspects of scheduling, for instance, a Mars lander under solar power timing constraints. As participants in the Quantum Networks Interagency Working Group, we have also contributed to the vision of quantum networks for the future. Quantum networks enable shared entanglement at long distances, which would support long baseline telescopes that take advantage of quantum interference and quantum sensor arrays, including gravitometers. A quantum network with entanglement swapping would support connecting quantum processors via quantum channels, enabling multiple processors to act as a single, much larger and more powerful quantum processor. It also enables smaller quantum processors to interact with larger quantum processors for secure processing, such as blind quantum computation. QIS is a rapidly emerging field, as we all understand, with a lot of promise, but also with enormous challenges. In order to advance the field and actually make an impact, we cannot do it alone. So here are some examples of major partnerships that we have in quantum computing. They run the gamut of other US federal agencies, major companies, and international partners. For example, we work very closely with DARPA, DOE, and AFRL on implementing optimization algorithms on NISQ devices and compare against classical approaches. We provide unique expertise in quantum algorithms, applications, and tools, and increase the understanding of quantum behavior and refine strategies for quantum advantage. And we analyze fundamental mechanisms for optimization and sampling, including population transfer. As I said earlier, we work closely with companies such as Google and Rigetti, where we are assessing their gate-based processors for meeting complex computing challenges. We are developing calibration and noise modeling approaches, as well as working on the DARPA scheduling applications and advanced mixers project with Rigetti. And finally, we also have major collaborations with international partners such as DLR, where we are developing open source software library for use of quantum computing in space applications. And we had worked with them on quantum algorithms to assign flights to airport gates at Frankfurt Airport to minimize passenger transit time. And recently, we have signed an agreement with the Australian Research Council Centre of Excellence on quantum computing and communication technology, where we expect to further understanding of quantum technologies and potential applications. Before I conclude my presentation, I wanted to leave you all with some key takeaways from my perspective. Understanding and harnessing the power of quantum computing is a formidable challenge that will require many things, such as new insights into physics, mathematics, and computer science, breakthroughs in engineering design to produce robust, reliable, scalable technologies, innovative algorithms and tools in computer and computational science, and finally, a diverse workforce with appropriate expertise to leverage this new paradigm. But even without all these challenges, the future is exciting in quantum computing because small-scale universal quantum chips are becoming available, new and better quantum algorithms and quantum heuristics are emerging, and compilation and performance capabilities are improving rapidly. And here I wanted to show this little quote from Wikipedia about the ENIAC, the first general purpose computer. And if you look at some of those things that were the challenges with ENIAC, those are the same things that are challenges with quantum computing. Figuring out how to get it into the system, and then followed by a period of verification and debugging. This is no different what we did in high-end computing or supercomputing, decades ago. We are doing the same thing with quantum. And then bringing it a little bit closer to home and a historical tie-in to my own NASA center, the ILIAC-4 was brought to Ames in 1972 by then Center Director Hans Mark. And it is considered the world's first massively parallel supercomputer, but it had only 64-bit floating point units and a single CPU. And it ran in the SIMD mode, single instruction, multiple data, and it only had 50 megaflop speed. And finding appropriate problems and algorithms were extremely challenging. And those are exactly the same challenges we are facing today with quantum. And questions were raised at that time. How broad would the spectrum of applications be for massively parallel computations? And will computers ever be able to compete with wind tunnels? And those are the same questions we ask today. So I'll end here. Let me finish by showing a picture of Ames, as well as of our QuaIL team in a Zoom setting now that we've been in a pandemic for 1+ years. And again, I'll say that if you're interested in more information about the R&D work that is going on in our group, here are a couple of overview articles. And with that, thank you very much for your attention, and I'll turn it over to Lawrence. Thank you.
Thank you, Rupak. That was an excellent presentation. Thank you so much for your time. Ladies and gentlemen, just to let you know, this is a pre-recorded session, but if you have any questions for Rupak, leave them in the chat function, and I will make sure that they are passed on to him if relevant. Thank you, Rupak. Thank you so much for your time. I appreciate you doing the keynote today.
Thank you.